Steel. It's a fantastic material, we see it everywhere. It builds our modern world, from tiny screws to giant bridges. But raw steel isn't always perfect. It often needs a little help. We can make it much better, stronger, tougher, or even softer. How do we achieve this transformation? The answer often involves fire and some very clever cooling. This amazing process is called heat treatment. It might sound pretty simple, just heating and cooling metal. But trust me, it's powerful science. It changes steel fundamentally right down to its atoms. Think of a master chef in a kitchen. They start with good basic ingredients. Then, through skill and precise cooking, they transform them into something incredible. We do something very similar with steel, using heat, control, and knowledge to create truly super materials. This essay is your backstage pass. We're going to explore these fiery secrets. You'll understand how these processes work, and more importantly, why they matter so much. So, what exactly is heat treatment? It's a carefully controlled process, a sort of cooking recipe for metals, especially for a versatile metal like steel. We heat the metal to specific temperatures, then we cool it down again. All of this is done very precisely. Every single step in the sequence matters. The timing, the temperature, all critical. It's a science of thermal manipulation. Why do we go to all this trouble? The main reason is to change the steel, to alter its physical properties, and sometimes its mechanical properties too. Properties like its hardness, for example, or its toughness, which is impact resistance, or even how easily it can bend. We want to achieve specific desired results, tailoring the steel for specific jobs. Steel, as you might know, is mostly iron, but it also contains a little bit of carbon. Heat treatment works by shuffling these atoms. The heating and cooling cycles cause the iron and carbon atoms to arrange themselves into new internal structures. These microscopic structures define the steel, they dictate how it behaves under stress, and ultimately, how strong or ductile it is. This refined control gives engineers immense power, the power to customize steel effectively. Now let's talk about a process called annealing. You can think of annealing as a kind of spa day for steel. Its main purpose is to relieve internal stresses. It also makes the steel much softer. This is often a vital preparatory step, setting the stage for what comes next. How does this gentle process actually work? First, we carefully heat the steel. We bring it up to a specific high temperature. This temperature is above its critical point. We then hold it there for a certain period. This soaking time allows the tiny grains inside, the very crystals that make up the metal, to relax, reform, and become more uniform. It's like smoothing out all the wrinkles. Then comes the cooling phase. This part is super important for annealing. We must cool the steel very, very slowly. Often this is done right inside the furnace. The furnace is turned off, and the steel cools down with it. This extremely slow cooling is crucial. It prevents new internal stresses from forming. It ensures the steel remains soft and wonderfully easy to work with. Annealing, therefore, prepares the steel perfectly for its next manufacturing adventure. Section 4, Quenching, the big chill for super strength. Alright, now for something much more dramatic. Let's talk about quenching. This process is the polar opposite of annealing's gentle, slow cool down. Quenching is fast, incredibly fast. It's a real shock to the system. For the steel, that is, not for us. But it's usually a very good shock, one that imparts amazing new properties, specifically extreme hardness. First, just like with other treatments, we heat the steel to a precise temperature. This is typically a high austenitizing temperature, hot enough for the carbon atoms to dissolve fully into the iron crystal structure. Think of it like sugar dissolving in hot tea. Everything gets mixed up very nicely, the carbon is evenly distributed. Then, the really exciting part begins. Bam! We cool the steel, and we do it super rapidly, usually by plunging the hot steel into a carefully chosen liquid bath. Water is a very common quenching medium. Oil is also frequently used for a slower quench. Sometimes, special polymer solutions are employed. This incredibly fast cooling traps the carbon. It doesn't have time to precipitate out. It gets locked into a new, strained structure. This new, super hard structure is called martensite. Section 5, Tempering, finding the sweet spot after the shock. So, we've quenched our steel, it's now incredibly hard, super hard. But, as we just learned, it's often too brittle. Imagine a hammer made of glass. It would be very hard, yes. But it would shatter on the first strike. That's not a very useful tool, is it? So, we nearly always need another step. This crucial follow-up step is called tempering. It's all about refining those properties. Tempering is designed to reduce that brittleness. It makes the steel significantly tougher. Toughness is the ability to absorb energy, to resist shocks and impacts without fracturing. We take the hard, freshly quenched steel, and we carefully heat it again. But this time, not nearly as hot. We heat it to a much lower temperature. This tempering temperature is precisely controlled. It varies depending on the desired outcome. We hold the steel at this tempering temperature for a specific, calculated amount of time. This allows some internal changes to occur. Then, we let it cool down. Usually this cooling is done in still air. This reheating and holding process relieves some of the internal stresses that were introduced during the rapid quench. Section 6, Real-World Steel, where heat treatment shines. So, where do we actually see these processes? Annealed steel, for instance, is all around us. Think about the steel sheets used for car bodies. Those panels need to be pressed into complex shapes. Annealing makes the steel soft and formable, allowing it to be shaped without tearing or cracking. It's absolutely essential for auto manufacturing, and for many other sheet metal products like appliance casings or ductwork. What about electrical steel, the kind used in transformers and motors? That steel is also often annealed. This improves its magnetic properties significantly, and it helps to reduce energy loss. Steel wire is another great example. It's annealed so it can be drawn thinner and thinner to make cables and ropes, or even the strings for musical instruments. Annealing makes it ductile enough for this. Now, quenching and tempering. This dynamic duo is a true workhorse. Tools of all kinds rely on this treatment. Think of chisels, hammers, and axe heads. They need a very hard cutting edge, or a hard striking face, and also a tough body to back it up, to withstand repeated heavy use without failing. That's the magic of quench and temper. Knife blades are another classic example. Section 7. Conclusion, Forging the Future with Fire and Finesse. So there you have it, folks, the fascinating basics of heat treating steel. As you can see, it's not black magic. Though the results can seem magical, it's actually clever material science combined with careful, precise engineering. We take what is already an ordinary useful steel, and we transform it into something extraordinary, all through the controlled application of heat and specific cooling methods. Let's recap the main players. Annealing makes steel soft and workable, more ductile, less stressed, easier to shape. Quenching, on the other hand, makes it incredibly hard, by rapidly cooling it to lock in carbon, creating that special martensitic structure. But this extreme hardness also makes it brittle, and that can be a significant problem for many practical uses. Tempering is the elegant solution to that problem. It's performed after quenching. It skillfully reduces that brittleness. It adds crucial toughness to the steel, while still retaining much of the desired hardness. It's all about finding that perfect balance, the ideal combination of properties, for the specific job the steel has to do. Mastering this is a critical industrial skill.